In this chapter, what we are going to see is stability analysis and root locus techniques. Stability analysis and root locus technique. Here, this x1 of t is output, x-axis is time, y-axis is output, x1 of t. The output is decreases, finally settles at 0. So this signal can be called as bounded signal. It has limits. Within that limits, so bounded signal. A step signal, if you take up to infinity, it is within that bounded signal. A sinusoidal signal with constant amplitude, again bounded signal. Here, e power at, if you take, this is e power at, go on increases, exponentially increases. This is unbounded signal. It will go to infinity. This will go to minus infinity, minus e power at. This will go to minus infinity. This is unbounded signal. We see that this is sinusoidal signal, but its amplitude go on increases. E power at sin omega t. E power at sin omega t. Its amplitude go on increases. Unbounded signal. Again, unbounded signal. So these are all examples for unbounded signal. If the output of the system is unbounded, then the system is unstable. If the output of the system is unbounded, if you plot the output of a system, it is looking like this. This is output of a system. Its output is plotted. It looks like this. This is an unstable system. This is marginally stable because it is neither settles nor increases. Marginally stable. This is stable system. This is stable system. This is unstable system. Unstable. Stable. Stable. Marginally stable. Unstable. If the system's output is like this, the system output is like this, we can say that this is stable system output. This is stable system output. This is marginally stable output. The system has marginally stable output. This is unstable output. This is also unstable output. Our system itself unstable. System itself, that's why it gives unstable output. The system is unstable, that's why it gives unstable output. In other words, the system is unstable, that's why it gives unbounded output. We must say like that, unbounded. It is not bounded signal, unbounded. Unbounded output. Unbounded output. Unstable system gives unbounded output. Then what is the definition for stability? If we give a bounded input, we know what is bounded input signal. What should be how it should look like. Bounded input signal is given. The output also should be bounded. Then the system is said to be BIBO stable. Then the system is said to be BIBO stable. Bounded input, bounded output stability. The system is said to be bounded input, bounded output stable. A stable system, for that I am giving bounded input, it gives bounded output. Then the system is said to be stable. I am having an unstable system. For that I am giving bounded input, it gives unbounded output. Because the system is unstable system. The system is unstable system. That's why for a bounded input signal, it gives unbounded output. Unbounded output. Therefore, it is an unstable system. bounded. For an engineer, what is bounded input? I'm not talking about signal. What is bounded input? All for mathematician, if it is not infinity, then it is called bounded. If it is less than infinity, mathematician will say that bounded. What is bounded signal? Bounded signal means he will say if it is less than infinity, then it is bounded. He can say. But for an engineer, how you can say it is bounded signal, bounded input? All measurable inputs are bounded inputs. All measurable. If it is infinity, we cannot measure. So all measurable inputs are bounded inputs. If the output also measurable, then it is bounded output. So for a bounded input, the output also bounded means it is a stable system. For a bounded input, if the system gives unbounded output, then it is said to be unstable system. Mathematically, how we can explain VIBO stability? What is C of S? C of S equal to input is R of S. Therefore, I can say that G of S, R of S. Because R of S is input, C of S, G of S is the system. That's why C of S output equal to G of S multiplied by R of S. What is C of T? Multiplication in frequency domain is convolution in time domain. Convolution in time domain. That's why we can say 0 to T. 0 to steady state value means infinity we have put. So let us put infinity R of G of T, G of tau, R of T minus tau, D tau. Convolution in time domain. Convolution in time domain. What is BIBO stability? Bounded input. R of T minus tau is bounded. R of T minus tau is bounded. That is R of T is less than M, less than infinity. It is measurable quantity, M. R of T is measurable, bounded input. Therefore, what I can write is if C of T, modulus of C of T equal to modulus of C of T equal to modulus of integral of 0 to infinity G of tau R of T minus tau D tau. This must be less than infinity. It must be less than M, less than infinity. Then it is said to be bounded. The system is said to be bounded. The final output must be less than infinity, measurable quantity. But we know that R of T is bounded, that is less than M. So we can say that it is less than or equal to integral of 0 to infinity modulus of G of tau modulus of R of T minus tau T tau. This we know mathematically. Inequality equation. If modulus is breaking down, then it must be less than or equal to G of tau R of T minus tau D tau. Or we can say that less than or equal to, this can be replaced by M because it is less than M. R of T is less than M. So it can be replaced by M. Therefore, M integral of 0 to infinity modulus of G of tau D tau. You can say like that. If when this will be measurable, M is measurable already. M is already measurable. If this is also measurable, if this is also measurable, then the entire quantity C of T is measurable. C of T is measurable. If this is measurable, this is bounded, then C of T is bounded. What is this? The integral of 0 to infinity G of tau D tau is, what is this? It is this is nothing but impulse response. This is nothing but impulse response. It is nothing but impulse response. What is impulse response? R of S equal to what? For impulse input, R of S equal to 1, R of T equal to del of T. For R of T equal to impulse input, then R of S equal to 1. For that, it is integral of 0 to infinity del of T. Let us assume that in that case, M becomes 1. M becomes 1. So this becomes this modulus of C of T must be less than or equal to this. It means this impulse response must be bounded. Impulse response must be bounded, or integral of G of T dt must be bounded. Integral of, both are same. Integral of G of T dt must be bounded for a stable system. For a stable system. In frequency domain, we need not check for BIBU stability. We need not check integral of G of tau d2. We check where is the location of poles. Where is the location of poles? If it is on the left-hand side, we can say that the system is stable. If it is on the left-hand side, we can say, if the poles are in the left-hand side, we can say that the system is stable. Therefore, we must know what is poles. Already we have seen a review of poles and zeros. Poles, what are poles? Poles are roots of denominator polynomial. In other words, suppose D of S is the denominator polynomial, equate to 0, find the roots. That is called poles. What is zeros? N of S is the numerator polynomial, equate to 0, find the roots. These are all zeros. The zeros of system are roots of the numerator polynomial. So if poles are in the left-hand side of S plane, this is S plane, this is S plane. If the poles are in the left-hand side, then the system is said to be stable. If the poles are on the right-hand side, system is unstable. Poles on the right-hand side. But zeros can be on the right-hand side. How zeros are represented? Suppose I am having 1 0 here, 1 0 here. Zeros are represented by circle. I am having 1 0 here, 1 0 here. So definitely a complex conjugate will be there. 0 will be represented like this. Poles will be represented by cross. Pole is represented by this. 0 is represented by this. This is another 0. This is another 0. Zeros are represented by dot and circle. Poles are represented by X. Poles are represented by X. So if the poles are on the left-hand side, then the system is said to be stable. Find the poles and zeros of the transfer function and plot on a S plane. Find the pole. Poles are -4, one pole. Then another pole is -6 plus or minus square root of 4AC divided by 2A. -4 4J -3 plus or minus 4J. So these are the poles. Zeros are -1, -2, -1, -2. In a S plane. So -4 at this point, one pole. Another pole is -3, -4. So -3, -4. Here one pole. So here one pole. Zeros are at -1, -2. This is called the pole zero plot. Pole zero plot. Find the poles and zeros of the transformation. Sketch the pole zero plot of the system. Another system. Here, the poles are 0, 0, minus b plus or minus square root of b square minus 4ac. Divided by 2a. So what are the poles? 0, 0, minus 2, minus 3. Zeros are -1. So what is the plot? -1, -2, -3, sigma j omega. Here the -1, 0 is there. At a -2, one pole. At a -3, one pole. This is asked how to represent repeated poles. At 0, 2 poles are there. One pole means you can put like this. How to represent second pole? We have to draw like this. 2 poles are there. Here, repeated poles. 2 poles. 2 poles are there. We have to mark like this. That's why this is. Other poles are simple. So repeated poles has to be marked like this. Why the system becomes unstable? Because pole on the left hand side means, suppose I am having a system with S plus A. A by S plus A is the system. If you take an impulse response, G of S equal to this. R of S equal to 1. What is impulse response? Impulse means what? Hammer blow. That is R of S equal to 1. For that, what is the output? C of S equal to G of S multiplied by R of S. G of S multiplied by R of S. That is equal to A upon S plus A. A upon S plus A. That is equal to C of t equal to what? We have to take Laplace inverse. A e power minus at. If it is in the left hand side, you will get e power minus at. If it is a by s minus a, what you will get? C of t equal to a e power plus at. Plus at means what is the response? The response go on increases. Unstable. That's why this pole must be on the left hand side. Here, what is the response? It comes like this. This is a e power minus at. This is a e power plus at. Go on increases. That's why pole must be on the left hand side. Here, the pole is on the left hand side. The pole is on the left hand side. The response you see bounded. Here, the pole is on the right hand side. You see that go on increases, unbounded. Here, the pole is at the origin. What is the response? Step out. 1 by S. The system is 1 by S or A by S. A by S. Impulse response is step out. Here, magnitude bounded. Magnitude bounded. But if you see the energy, if you integrate up to infinity, energy becomes infinity. Energy becomes infinity. If the magnitude is bounded, then we can say the system is stable. These are all what we have taken is real poles. Real poles, no oscillation. If we take a complex pole, 2 poles are there, second order system, left hand side, it oscillates, but finally for impulse input, all are for impulse input, not step. Impulse input. Impulse input means giving a blow, giving a punch, that's all. After that, initially it's rest. If we give punch, oscillates, finally it comes to rest. So it oscillates, finally it comes to rest. So it is stable system. Here, the poles are on the right hand side. If we give a punch, what will happen? Its amplitude go on increases. Unstable system, unbounded output. Unbounded output. This is bounded output. Bounded output. Here, always oscillating. The poles are exactly on the J omega axis. The S plane, these are all S plane. This is also S plane. S plane. Poles are exactly on the J omega axis. Sustained oscillation. This is called marginally stable. Marginally stable. Suppose I'm having 2 poles, repeated poles at the axis. Repeated poles on the J omega axis. Then also it is unstable. If 1 pole is on the J omega axis, no problem. Marginally stable. Oscillation, marginally stable. If repeated poles are there means, then it is unstable. Unstable. Repeated poles. That's why amplitude go on increases. Amplitude go on increases. All are impulse responses. All are impulse responses. All are impulse responses. Means R of S equal to 1, not 1 by S. So if the roots are in the left half of S plane, integral of 0 to infinity G after dt will have a finite value. The system response will comes to 0. The system is stable. The roots of the characteristic equation lie in the left half of S plane. Then stable system. The roots have positive real part. Positive real part. That is the right hand side. Its the integral of G of tau d tau is infinite. Unstable. Non-repeated roots on the J omega axis. Non-repeated roots on the J omega axis means sustained oscillating. It will oscillate forever without increasing amplitude. That is called marginally stable. That is called marginally stable. If repeated roots means unstable, unbounded output, unstable. Unstable. Repeated roots on the J omega axis. Repeated roots on the J omega axis, unstable. This do it yourself. Discuss the stability of the following system. Check the note down, and check the stability of these systems.